Okay, good morning everybody. Around this time, most years I stand up and talk about stuff that we've done over the last year and try and impress you with all the great advances we've made in the last 12 months. But came to this point now and we realised that over the last 10 years we've done a lot of work on arrays. It's perhaps a good opportunity to review what we've done over the last 10 years. And so it's going to be a very quick summary, so we're going to try and cover a lot of slides in this time. And so just bear with me if I end up speaking quite quickly. So tried to separate it down into 4 areas. So wave tank testing, physical testing, numerical modelling, analysis of results, and then guidelines which we tried to put together as best we can. So within the wave tank modelling, we've done a variety of tests, some very large scale tests. So this is a device, a set of heaving buoys we modelled with 24 different heaving buoys. We tried a number of different arrangements to look at how they worked, interacted. We also looked at a small arrays of oscillating water columns. We used oscillating water columns partly because one of the things we found with the heaving buoys was that the performance of the heaving buoys varied. It's quite hard to get a mechanical system to be consistent, so we moved to, if you like, a more solid state type system where we just use an orifice to damp or to extract the power to damp the motion of the water column, and so therefore reduce to some extent the uncertainty, which we'll come on to. The other thing we've done is to do a lot of mapping around the oscillating water columns in this case. So you can see here on the left an array of wave probes which we then moved up along through the tank, which we were able to get some nice maps of the disturbance due to the array. So these are attenuator arrays here on the top, and you can see the interference pattern at different frequencies, and then the bottom row is a terminator type array, and you can see a difference in interference pattern due to particular devices. And I haven't shown them here, but also depending on the amount of energy you extract, depending on whether you extract it at optimum energy or overdamp it or underdamp it or indeed don't damp it at all, then you get different interference patterns or intra-array patterns. So here's an example of here where we go from fully reflective, so we've basically closed it off, to an overdamp situation where we've created overdamping of the water column, and then an optimally damped. You can see there are changes in the radiation patterns around each of the devices there, each of the oscillating water columns. And we also looked at a number of different arrangements, so as I said earlier, terminator and attenuator configurations, as well as diagonal configurations and chevron type configurations, and looked at the way that the disturbance changes depending on that configuration you've got around the different devices. One of the things I said that we noticed is that one of the challenges is to generate performance in your array which is consistent. So we've done a lot of work at looking at the variability of the performance in an array. So here we've got small 4 device array, and here's the power capture that we measured. And you can see, you would expect, these are long-crested, in long-crested waves, and you'd expect 1 and 2 to have the same power capture, and 3 or 4 to have the same power capture, assuming that the system is perfect, as you would tend to assume in a numerical model. What you find actually, because of small imperfections and variety of experimental effects, that you do get a variation. And here on the right you can see here's the one standard deviation, 2 standard deviations, uncertainty in the performance in the power capture. So you can see there is some confidence there's a difference between the first row and the second row, but it's not necessarily as large as you'd hope, because if you really wanted to guarantee at more than 95% confidence, the very bottom ones of these will obviously overlap with the top ones of those, and so therefore you could argue that statistically it doesn't prove that there's any array interactions. So we look at that in a variety of different ways. So we looked at the possible causes of that without going into any detail. So there's obviously a spatial variation. Everybody who works in wave tanks know that in certain points of the wave tank, the wave is not the same as in other points in the wave tank, and that can vary with frequency, and also varies whether you've got a device in the wave tank or not. So you can happily map your tank and think you understand the variations, but then you realise that actually when you put your device in, the variations then change. You have a temporal variation, so when you repeat the test a second time, it's not necessarily the same as the first time. for whatever reason. That's clearly a problem if you put your one device in and you test it, then you take the device out and put it back in again. You won't get the same result, even if it's nominally exactly the same configuration. You get spectral variability in the sense that if you're testing in irregular waves, the different phases between the wave components in the spectra influence the power capture in a nonlinear system. Obviously this is real life, so all the systems are nonlinear. So there's an issue there. So if you don't test in exactly the same wave train series, you'll get a variability. You also get issues of model repeatability, in the sense the same model may not respond in the same way. This is where we move to a solid state system. So if you like, we used air bearings on the heaving buoys, but sometimes, for whatever reason, there may be a bit of dust or grit or something got into the air bearing, that would change its response. And you get reproducibility. So you may ask the workshop to make the model exactly the same, but you find that the model itself differs as a result of manufacturing tolerances which exist. And then within the numerical model itself, you also have sort of discretization errors as well. So all these things you need to think about when you're looking at validating your array model. So moving on to the numerical modelling we've done, very quick thing we've done on time domain model. I think David has done a lot more. He'll be talking next on time domain modelling, but we've done little bits and pieces on time domain. We also looked at developing a technique we call spectral domain modelling, where we use a random phase assumption between the wave components in the array in order to produce an estimate of performance within the array, which is faster than the time domain model, but allows the inclusion of some non-linearities which you can't get within a frequency domain model, which is more commonly used. So we compared these to some of the physical tests we did previously that I showed for the heaving buoys, and you can see that there's the reasonable similarity between the spectral domain model and the physical testing. That's on a ray scale, if you like, the full farm scale. On an individual C state, you can see that there's still some similarity, though similarity deteriorates a little bit. And then on an individual device basis for a single C state, you can see that there is some similarity. If you look at the numbers on the left-hand side, they tend to be just above 1, as you find the first row in a wave array tends to capture more than the isolated device on its own. And then it dies away as you go towards the right-hand side. So in this case, the waves are coming from the left-hand side. Just one thing to note here, the numerical model is nice and symmetrical as you would expect because we haven't added any kind of perturbation associated in the y direction. But you can see in the physical system, we have variations here. If you just take the first row, you may expect these because it's symmetrical to be the same, but we're getting around about a 6 or 7% difference between those two. And that's the kind of level of uncertainty you need to deal with when you're looking at physical wave tank testing. So you've got to be aware that if you're looking for a difference in your array interaction of 5 or less %, you're going to struggle, or you need to design your experiments very carefully in order to identify those effects. We also looked at some Booz-Ness wave modelling, where we modelled the wave tank completely, including the beach and the wave paddles and the sides, which aren't completely parallel in our wave tank. We used some sections to try and channel the wave into a better formation. And you can see here again between the experimental and numerical data, we're getting reasonable amounts of similarity, at least on a qualitative basis. And they also looked at using spectral wave models to model wave arrays, which obviously is beneficial. Using very large arrays of hundreds of devices, it becomes more and more problematic when you start to use especially a boundary element method type solver. And so in this case we've used a spectral wave model to propagate the waves in between different devices, and you get some results which seem reasonable. Again, qualitatively seem reasonable. We have had some success comparing it to the wave tank data, but that's still an ongoing work in order to get the response to the device correct, or the characteristic of the device's source term, which the device is represented by, correctly modelled in our spectral wave model. This is actually the one slide about the work we've been doing recently on Cochin functions. One of the parts of the The spectral wave model is if we can represent the way that the waves are re-radiated and diffracted by each individual device, and we can more accurately represent the redistributed energy. And one of the questions we have is, how reasonable is the phase averaging approximation which we make within our phase average spectral wave model? And clearly, array interactions are fundamentally phase dependent. But if you consider a spectra, and as well as, so you have not only a frequency variation but also directional variation, and to compare these two cases, you can compare a boundary element method here and a phased average Cauchy function type method to represent the radiated and diffracted waves. And you can see that beyond this small area here, where you can see some phase dependence on the wave disturbance, actually it's very, very similar. So that's quite encouraging for the ongoing work. So looking at wave array analysis, so what can we do with these numerical and physical data sets that we've developed? So one of the things we looked at is over a sort of a whole range of C states in data. In this case it was EMEC, data at EMEC. We took the average of the 10 years wave data and considered if we had an ideally controlled pair of attenuators, what kind of power capture or change in interaction factor, I should say, can we achieve? And you can see that we get this type of pattern. The waves, again, this is in EMEC, the waves mostly come from the west-southwest, so you can see there's a tendency here that it benefits well from being an attenuator configuration. There's these 2 points here, which are roughly, I think, about 1.5 wavelengths apart, which represents these nodes. So even though we do have some variation within the spectra, the waves still do have a certain tendency to be concentrated in certain frequencies. We then want to look at the tuning necessity of an array. A lot of array assume you can control the system perfectly, and the question is, if you were slightly out in terms of your expectation of what the frequency of the instant wave was, or your separation distance, how critical is that? And we found here, we did some quick modelling, or relatively quick modelling, and looked at the effect of how the interaction factor is affected if we don't get our control perfectly right. And you find that even though the attenuator, in this case the terminator is doing better, but the attenuator is actually a lot more sensitive, tends to be a lot more sensitive, and it makes sense in the sense that what you're trying to do in an attenuator configuration is get the waves generated by the first device to constructively interfere with the second device, while the waves from the second device are also constructively interfering with the first device. Whereas one side by side, that's a less demanding control situation in terms of the phasings of the radiated waves or radiated diffracted waves, and so you get a broader bandwidth. So the sort of story there, if you like, is be careful about idealized array interactions. This is another thing we looked at in terms of optimum motion. Again, a lot of times array models will assume that there's no motion constraints because they allow rapid estimation of performance if you don't add those sorts of complexities to the model. Here we found that actually in the terminator array, two devices side by side, the interaction factor and power factor goes up and down together pretty much in sync in the non-dimensional separation, so as you move them further apart, whereas in the attenuator configuration, you are getting an increase in interaction factor as you move the two heaving buoys together, but the amount of motion they require in order to achieve that increases. And indeed what you're effectively doing is creating a dipole or a cardio-type shaped radiation pattern. And so you're getting one device moving almost 180 degrees out of phase with the other, and so to achieve a dipole-type radiation pattern to increase the power capture. And that obviously requires more motion because you're effectively trying to destructively interfere with the waves moving out to the side. So something on significance of phase. Again, it's coming back to the issue about phase-locked interactions. And if we don't know exactly how well our phases can be controlled or how far apart our devices are, what sort of uncertainty or what sort of expectation can we get. So the red line is a probability distribution. So it's okay, we kind of know what our wave period is, give or take about a second. This is the peak or mean wave period or energy period. And then what can you say about the interaction factor? You can see here that you go away from these very sharp oscillations of up and down, which you get as the device moves in and out of phases. This is an untuned device, to something which is a lot more consistent. And if I can get to the next slide somehow. So you find, as I said previously, the upstream device, the first device, upwave device that you see, gets a small increase in performance due to the waves diffracted and radiated by the second device behind it. Almost like a second chance to capture that wave energy. The second device almost consistently loses energy, result of the amount of waves which are actually reaching it, because the first device has actually taken a lot of that energy out, either diffracted it away or otherwise. So moving on to guidance, very quickly, array effects, they're not as typically as big as you expect, normally around about 10%. If you take real cases into consideration, you're not considering these perfect array interactions. Simple things, perhaps maybe just worth reiterating, higher densities tend to result in larger interaction factors, so therefore, because most interaction factors result in reduction in power, tend to result in lower power capture. You obviously want to align them with the array, the way the waves are coming from. Smart configurations may be ideal in theory, but unlikely in practice. And in actual fact, our conclusion is that it's likely that the array layouts are going to be dictated more by physical considerations than actual power performance considerations. So something did within the WEC group, which I won't bore you with now. Thank you very much.
This production is brought to you by the University of Edinburgh.